Hello, everyone. Please join me in welcoming Professor Thomas M. Jahns from Wisconsin-Madison. So, it's a real honor and privilege to have him with us here. And if I go back to my personal experiences back in those days when I was sitting as a student back in India, I always thought and looked at University of Wisconsin-Madison. I said, oh, one day I'll be going there and do my PhD. Eventually I didn't, but that's a different story. But I always looked up to University of Wisconsin, and because of pioneers there in electric machines, power electronics, control, motor drives, and one of the pioneers have been Professor Jahns. So let me read his bio. So Professor Jahns received his bachelor's, master's, doctoral degrees in electrical engineering from MIT, Cambridge. Of course, we know where MIT is. Dr. Jahns joined the faculty of University of Wisconsin-Madison in 1998 as a Granger Professor of Power Electronics and Electric Machines. So he's a Granger Professor, and we are in Granger Auditorium. In the Department of Electrical and Computer Engineering, he is a co-director of the Wisconsin Electric Machines and Power Electronics Consortium, commonly known as WEMPEC, a university industry consortium with over 85 international sponsors. Prior to coming to UW-Madison, Dr. Jahns worked at GE Corporate Research and Development at Niskayuna for 15 years, where he pursued new power electronics and motor drive technology in a variety of research and management positions. His current research interests at UW-Madison include electric vehicle propulsion, renewable energy systems, microgrids, and energy storage. He is a fellow of IEEE. He received the 2005 IEEE Nikola Tesla Technical Field Award for pioneering contributions to the design and application of AC permanent magnet machines. He is a past president of the IEEE Power Electronics Society and the recipient of 2011 Outstanding Achievement Award presented by the Industry Application Society of IEEE. He was elected to the US National Academy of Engineering in 2015. So please join me in welcoming Professor Jahns.
Thanks so much.
Oh, before I forget, I almost forgot. I would ask ask Professor Gross to come up on stage, or here, and give this.
As close as we get to it, right?
So I would ask you to please give this.
This is for you. Thank you very much for coming to visit us, and we look very much forward to your presentation.
Thank you very much. It's my honor to be here.
Thank you, Professor Gross. It's all yours, Professor.
Thank you very much, Professor Banerjee. I really appreciate the effort that you invested in order to help make these arrangements and your patience during that process. But it's a pleasure to be here, to have an opportunity, especially given the fact that it gives me an opportunity to talk about one of my favorite topics. Before I get into that topic, let me just remind you where I come from. Perhaps some of you are aware of it. How many of you have been to Madison, or kind of okay, great. A lot of you have, but I see some of you haven't. So unlike some of my audiences where I have to say, Wisconsin is a state that's in the middle of the country, you have some idea, I hope, where it is. But Madison is a city that has maybe around 250,000 people. One of the special features about it is it's not only the home for the university, but it's also the state capital. And it was very fortunate to have it chosen as such a beautiful place because, as you can see, the capital is located just right at the center of a narrow isthmus between two lakes. Actually, there's a chain of 5 lakes that make up the group right around Madison. But here in the foreground, you see the heart of the University of Wisconsin. And I was thinking on the way down here that really there is a lot in common between the University of Illinois and the University of Wisconsin. I know there's a lot of competition out on the football fields, on the basketball courts, but frankly, there's a lot that we have in common. Both universities are in the same ballpark of the number of students. Both have major ECE departments. Both have major both power systems as well as power electronics and drives programs. So, as well as Professor Banerjee mentioned, we both have Granger. Actually, we both claim one of the Grangers, father and son, and the Granger Foundation has been very generous to both our institutions, and I thank them for their generosity, which has been very important to all of us here. So there really is a lot that we share in common. It's a real pleasure. I've enjoyed my visits here over the years to have a chance to meet not only the faculty but you, the students, as well. So with that as background, I'd like to say one more chart that let's see. have to point it in the right direction. Say a little bit more about WEMPEC. As you heard, WEMPEC stands for Wisconsin Electric Machines and Power Electronics Consortium, and the name really says a lot. It's a consortium that between industry and academia that really, as its name suggests, really focuses on machines and power electronics, and has done so for the last 37 years. So it's actually one of the older industry university consortium of its type that you'll find anywhere. We do have right now around 85 international sponsors, and what they all have in common is that they all are somehow involved in issues related to motors and in power electronics. There's about 9 faculty members, roughly 65 graduate students, as well as a number of off-campus students. And we're very proud of the fact that we're very international, and we try to keep the place as lively as we can by bringing in faculty from around the world. Because one thing that we all share in common, it's kind of like the area of health. I mean, we all have to worry about health issues. We all have to worry about energy, and that's one of the things I've always really loved about the field, is the fact that there are people worrying about the same kind of issues that we are, in some cases even more so in other parts of the world where energy is even more precious than maybe we consider it to be here. I would like to start out with a bit of motivation. I realize some of you in the audience are quite involved in power electronics and machines, some of you really not so much. So I am starting with some kind of introduction, and to those of you who know about this, please hold on, we'll take a deeper dive as we go along. But for those of you who are newcomers to say, well, hey, why are we talking about machines? Machines have been around for over 100 years. I mean, are they really, that's old stuff, and are they really that important? Well, to put in perspective, it's interesting to note that of all the electricity that's generated in the United States, over half of it is processed through motors. So it's really an incredibly important part of how we manage our electricity and how that's used. So, and especially when you then combine that with the fact that I am, and I hope that all of you are concerned about issues of looking ahead as far as greenhouse gases as it relates to climate change. Well, when you look at strategies of how do you deal with that, a lot of the sexiness goes along, and I'm subject to it too, to talk about photovoltaics and wind power on the generation side. But when you really look at it hard, you find that actually there's even more opportunity for making a major dent in the amount of greenhouse gases, at least comes from electrical sources, if we go after the uses and find ways in order to be able to use our electricity more wisely. Now, given the fact that we have over 50% of the electricity being used by motors, just kind of makes sense to say, well, maybe we should look at those and say, is there some way that we can achieve energy savings? And the answer to that is an emphatic yes. And that's not a new observation. This is something those of us working in the field have known for a long time. There are these things that are called adjustable speed drives. Go by different names, but I'll call them adjustable speed drives. And essentially, what they allow us to do, very simply, is to be able to take a motor, which you all recognize, and to be able to vary its speed, vary its torque. And by doing that, that makes it a very good match for a whole range of applications. You can imagine things like conveyor belts, obvious example of need to control speed. What may not be quite as obvious is that when you have pumps and fans, the need to be able to adjust their speed is typically taken care of, if you don't have an adjustable speed, by throttling or valving, and that ends up actually being an incredibly inefficient way to do that. There's really an incredible amount of energy that's lost there. If instead, rather than doing that throttling, we can instead adjust the speed, there's incredible opportunities for energy savings. Again, that part is not new. And frankly, adjustable speed drives is not new either. It's a concept that certainly has evolved a long way since the time when I first got into the business. I'm kind of dating myself back in the late 70s. Technology has come incredibly long distance. And in fact, there are a lot of drives out there, and they are making a significant impact where they're installed in saving amount of energy. Sad truth is that only a fraction of all of the applications that are candidates for this kind of adjustable speed drive are actually using them. So why is that? Why isn't everybody using it? If it's saving that much energy and it's doing such good things, why doesn't everybody use it? Well, let me count the ways. There are a variety of reasons that come up pretty naturally. Let's see, I guess I've got to hit the right one. That come up associated with it, and it's things like, well, surprise, adjustable speed drives cost too much. I mean, And you might say, but yeah, but there's energy savings. Over the life of it, you'll save money. But in the real world, too often, it's the first cost, the cost that it takes to install it, that ends up dominating, regardless of what the savings might be over the life. That's just the realities. And so as a result, that ends up being an obstacle. It takes up too much space, weighs too much, limited temperature range, and that's an issue because the machines are pretty tolerant of a wide range of conditions. Power electronics, not so much in terms of being able to handle the extremes of the heat as well as extreme colds, where in some applications, many applications where you need to tolerate that. Issue reliability is really important because obviously if you have something that is processing all the power for the machine, if something goes wrong in that drive, there goes your motor, there goes your production plant or whatever it is. So issues of reliability and fault tolerance turn out to be very important issues. And unfortunately, today's drives have not, in many cases, been able to meet that. So what do we do about that? I'm going to take a step back again, kind of 101 for those of you not familiar with the concept of power electronics. Power electronics is an important part of that key because that lies at the heart of those adjustable speed drives. Now, what is power electronics if you're not acquainted with it? Well, first of all, it's the class of electronics that processes power instead of information. That's, I guess, the first important thing to know. Second important thing is that power electronics processes electrical power from one form into another, maybe changing from DC to AC or vice versa, maybe changing frequencies. In this case, you might think of if we're taking fixed power at 60 hertz from the line, converting it into adjustable frequencies that we have to deliver to the machines, that certainly qualifies as something that really is well suited for power electronics. Power electronics is, again, this is mainly obviously for those of you who are not very well acquainted with it, is all around it. Is all around us. But one of the challenges we face for those who are in the field as far as getting respect for what we do is the fact that it's an embedded technology. That is, you don't see it. You don't buy a Tesla or almost anything because of the power electronics per se, even though it is, in many cases of these cases, the key ingredient that makes those things possible. In fact, one observation is that the very best power electronics doesn't weigh anything, doesn't take up any space, so how would you expect to be able to get much appeal for something that essentially is invisible, or at least ideally is close to being as invisible as possible? But in real life, we find that whether it be in something as big as this valve hall, stories tall, filling up this auditorium and much more, or something that you could pick out of your pocket, maybe some of you are staring at it right now, your cell phone, smartphone, those all depend on power electronics. There's so many other things in between that likewise have that requirement, whether we know or not. Lighting is an exciting area with LEDs. We wouldn't have those LEDs and we think of the LEDs, but we don't often think of the power electronics that lies behind them that makes those possible. So power electronics is already very important. If you say, well, you know, I'm not convinced yet that it's really that important, this gives you a little bit of an idea. These numbers are hard to come by, but the best guess right now is that today something on the order of 30% of all electricity that's generated in the US is processed through power electronics. The prognostications based on trends, given some of the things that are going on, including things we're going to be talking about in this lecture, talk about seeing that increase to levels of more like 80%. So that means that, 80%, 4 out of every 5 watts of electric power in the future, within your lifetimes, will be processed by power electronics. So it really is becoming, and it's been exciting in my lifetime to watch it go from a niche to something that in the future is going to be even more important in the future than it is today. So let's get back to, with that kind of introduction to the core power electronics, let's get back to talking about really the core of what this lecture is going to be about. Here's where we are right now. The vision that I'm going to present to you as far as one of the keys to getting to where we need to go in order to achieve this much wider acceptance of and implementation of this technology is a concept of integration. That is to take the need for this big separate box here and address the issues of too big, too much space, too much mass, and instead take advantage of what new technology is allowing us to do and to embed it right inside the machine. so that in the future what we'll see is something that really doesn't look much more different. It gets back to the point that I made. The best power electronics is power electronics that you don't see, that can be actually just absorbed into, in this case, inside the machine. What you see here is an example of really kind of the state of the art. You can see the machine, and if you look closely, there is a bump out here that represents where the power electronics is. But nevertheless, this falls short of where we can see ourselves getting to, and I'll be showing you more in order to clarify that. So given that, I mean, what do we need? What is missing? What do we need to do to get from where we are now to where we're going? Well, you're going to see a lot of the same things. We need to tackle the mass, we need to tackle the volume. Efficiency turns out to be very critical for a combination of reasons, including the heat that has to be managed within the device. Improved manufacturability, that goes very closely with the issues of cost, and finally the issues of reliability and fault tolerance. This is a pretty demanding set of requirements, and fortunately some of the tools for being able to do that are in the process of maturing as we speak. So the objective of this talk is to really present a vision for the future of integrated motor drives. Already started to do that by reviewing not only looking ahead, but also I'm a believer that it's worthwhile taking a little bit of a look behind to see kind of where we came from and put some of this in perspective. But the goal will be to be able to look to the future and use where we've already been to set the stage for where we're going. And in particular, I'm going to challenge you with a concept, particularly those who are in the field, with a concept that's based on actually taking a technology that frankly has been laid on a side road for quite a long time. Current source inverters is a promising technology in order to achieve that vision. But we'll get to that as we move along. I'm going to do that. Here's the outline, but it follows pretty much the pattern that the vision, the objectives I just described. A little bit look in the past. We'll use both some wider range and kind of use electric vehicles and hybrid vehicles as kind of the basis for really showing, I think, pretty vividly the progress that has already been made in this area, and use that as the launching point then to talk about the impact of so-called wide-bandgap power semiconductors, which again, some of you know a lot about, some of you not so much, so we'll talk about those, combined with the current source inverters, because it's really that combination that's really critical, and then finally conclude with some final comments about future directions and conclusions. So with that, let's start off with a little bit of a look behind. Actually, one of the earlier applications of integrating power electronics with machines is actually still with us today. Any of us that drives a conventional internal combustion engine vehicle, there's always an alternator there. Well, believe it or not, built inside there, again, you don't know it because it's built inside, is power electronics. What does it do? It adjusts the field in order to make sure that what comes out of that is regulated to be in the voltage range that we expect to have in vehicles. These are made by the gazillions. I mean, and frankly, I really respect it as being a tour de force, given the fact that this came out something on the order of 60 years ago when the technology was really very, very primitive compared to what we have right now. It's evolved, and so what we have today is really far advanced from that, but nevertheless, it's really testimony to just how long-lasting the concept of integrated motor drives has been around. And it's an indication of what can be accomplished, given the fact that this really is, even though a lot of people don't think of it this way, as one of the incredible success stories of this technology to date. Here's one that's at a very different extreme, but one that I admire. And so I picked this one out just because I ran into this earlier in my career. I can't take any credit for being involved in this, but this is aimed at a very specialized application for a military aircraft. But it's a case where by spending a lot of time and a lot of effort, it was demonstrated that even using the available devices that were available back in the 1970s, which are predominantly based on thyristors, four-layer devices, which I'll say a little bit more about later, take my word for it, much more primitive than what we have today. Yet the engineers at that time found a way to be able to take those. It took, in fact, altogether 36 of those devices wrapped around this machine in order to give it provide the capabilities of being able to give out or deliver a constant 400 hertz power, which is required by the aircraft, in spite of the fact that the engine speed was changing. So given the time when it was developed, it really, I see it as really a real milestone in terms of demonstrating what can be done in terms of the technology. Now, given this is a lot of money was spent, very expensive equipment, but nevertheless, it is a demonstration that even with the primitive technology of 40 years ago, that there were some incredible things that could be accomplished. Frankly, if we look at today for more general purpose applications, here's what passes for integrated motor drives. Sometimes they're referred by that name. And really, in some ways, it seems like a kludge. I mean, yeah, we got a drive in a box and we got some machine. Why don't we just kind of mount that box on the machine? There's your integrated motor drive. Well, that's a step in the direction, but that falls far short of the vision of what I have, because frankly, you know, I mean, it takes space and mass to accommodate the fact that we got these big bump outs that are mounted there. But nevertheless, this is what's out there, and I don't mean to minimize it. In some application, it turns out to be a very satisfactory and attractive solution. But frankly, it's not widely accepted today. There's real concern about, based on existing technology, whether the power electronics is going to fail first and therefore ruin the availability of the machine, and there's a variety of concerns, cost, and all the ones that I described. So this is a step on the way of where we need to get to. As I mentioned, this is an example of one of the more, what I give credit is one of the more advanced schemes. It still doesn't have the full integration, but nevertheless is a step forward in terms of, you know, of tighter integration between the two. This is used in factory automation applications, really pretty clever. The idea is that by performing this integration, we no longer would have to have all the drives mounted in a cabinet with each one of these machines in a processing line, each having multiple three-phase lines. Instead, the idea is we can just daisy chain these together, provide DC power to all of these, and do all of the conversion from that DC to AC locally, rather than having it being done back in the cabinet. So this is a case where the integrated motor drives was attractive because it solved a system issue, and it has been quite successful, albeit in kind of a niche area. It's initially done by Indramat and part of Rexroth, and has since been adopted by other manufacturers. So with that as kind of background of where we are right now, as I said, I'd like to use automotive as to give you a little bit of an idea of the evolution that's occurred. If we go back to the Toyota Prius, this was at a time where you can see separate drives, separate machines, in fact, two of them inside this so-called split system here. You can see the big orange cable that's connected. Only a few years later, in roughly 2004, this came out, really, we're celebrating about the 20th anniversary when the Prius first arrived on the scene. A few years later, Aisin, who's part of the Toyota family, worked with Ford and developed this scheme here where you can see the controller here mounted under this black shroud here is mounted right on the machine, eliminating the need for these heavy power cords. Power cables, I should say. And sure enough, buried underneath, you can see where the power electronics is located, shares cooling, and represents, again, a step in the right direction in terms of performing the kind of integration I've described. I'll go through these quickly. Nissan, if you go from the original Leaf, 2 years later, they got rid of the big heavy power cable there. You can see what it meant in terms of the integration, and certainly some significant cost saving, because often, believe it or not, some of the most unreliable sources, the greatest sources of unreliability can be just connectors by themselves. So what do? Eliminate the connector or make it much simpler. This is a little bit of a sidestep because this is not in wide use, but nevertheless, for those of you who haven't thought about it, why is it that we need to have one electric machine under in a drivetrain? Why couldn't we perhaps mount a motor in each wheel? That way we could have independent control of all four wheels. Think of the maneuverability and all of the good things that you could get from doing that. Again, not a new idea, but you can imagine that if you follow what I've been describing, if you can mount the machine in the wheel. This is a company by the name of Protean that I give them credit for being pretty gutsy in proposing an approach in which they not only had the motor mounted in the wheel, but the power electronics as well. Now, the reason I'm saying that with a little bit of surprise is because of the fact, imagine how difficult that environment is. I mean, going over bumps, the temperature extremes, water through puddles and whatnot. The idea of being able to do this is very challenging. And frankly, Protean has had to adjust some of their plans to be a little bit less ambitious. But nevertheless, it's an indication of what some people are thinking about and what some young companies are willing to try in order to explore the limits of what technology can do. And as a technologist, it's great to see these things come along. Talking about something that's a little bit closer to home, I know that the University of Illinois is proud of its connection to the very origin of Tesla. This is the Tesla S, which until a couple years ago was really the flagship. If you look, we're to take the body, the machine of the vehicle away and look at what's underneath there, here's what you see as far as the heart of it. There's a gear train. You've got these two cylinders here. And at first you'd say, well, it looks like it must be a dual machine because they look almost as if they're the same, but it's not. It turns out that one of them is the machine, the other one is the inverter designed to be able to fit inside this cylindrical case. And so again, it's a step on the way to coming up with a more integrated kind of configuration. In this case, an integration of the machine, inverter, and the gear train that's needed. In fact, there is an option for an all-wheel version which has a similar kind of configuration on the front wheels as well. Let's bring it to even more recently. Just within the last year, the Tesla 3 is making noise in terms of its development. You don't hear as much talk, only among those who are interested as far as what the technology is. They deserve credit of being the first production battery electric vehicle in the world to adopt silicon carbide switches. Again, some of you, that'll mean a lot. We're going to be talking a bit more as we go along about the adoption of a different type of power semiconductor material, silicon carbide, instead of conventional silicon, which has been the basis of all electronics really for the last 60 years. Tesla demonstrated their willingness to give it a try by adopting a new technology. And in fact, as you see in this lineup here, within this box is where this power electronics is located. So you can see that they are taking a step in terms of not only shrinking the size of the inverter, but also more intimately mounting it on the machine. So you can see the evolution that brings us right up to where we are today. Siemens is another company that in a couple special editions of Volvos has introduced their own technology, which again is pushing the limits in terms of integrating the power electronics more intimately. You know, it's still, again, you can kind of see a bump out, but it is getting to the point where it's progressively getting smaller and smaller. And by the way, they are doing some pretty eliminating the need for all these wire bonds that are the basis for conventional devices, and instead adopting a technology that instead eliminates. So there's a variety of advances, some obvious, some more subtle, but still very important, that are going on in order to be able to get to the point of introducing something like this, because this implies that they're addressing all of these issues having to do with operating in challenging thermal as well as vibration in environments. Just to change the topic, it's not only on the ground. This is just one short chart. Actually, Professor Ron is here in the audience. There's a number of us that are working now in the area of actually doing the same thing with aircraft that has already happened with automobiles. That is the concept of hybridizing it. And in some special cases of eliminating the jet engine altogether and going all electric. A lot of the motivations are the same, and the only reason I'm introducing it just to indicate that power electronics and this concept of integration actually applies not only on the ground, but actually is being investigated for applications in the air as well. Why? Well, again, aircraft is really kind of the poster child for an application where volume and mass mean a whole incredibly big amount of money in terms of its value if you can reduce that. So any step that you can take, such as this kind of integration, if successful, will be a big step in terms of helping to make that technology a more reality. There's plenty of challenges that go along with this technology, and this is just one of them. What I'd like to do now is, with that as kind of background, really bringing us up right up to the very edge of where we are today. What is this vision and the challenges I'd like to raise? And I don't think you'll be surprised. I have already exposed my major concept, but just to crystallize it, the basic concept here is to be able to get to the point where the power electronics is integrated right inside the machine. This is typically the terminal box, but whether it's integrated here or whether it's integrated in the end bell, the bottom line is if you look at the machine, it won't look any different from the way that it looks right now. So it's anticlimactic in one sense. But on the other hand, it's a real tour de force if we can get to the point where you can buy this machine. It not only can spin at one speed, but it gives us the ability to be able to provide, have the adjustability and speed and torque that unleashes the opportunity for the incredible energy savings that I described. Of course, how are we going to communicate? Well, of course, these days you wouldn't do anything other than communicate wirelessly. So again, it's no extra wires or whatever that you need. It all just essentially looks like the kind of machine. It's just that you can pull out your cell and be able to tell it change speeds or whatever it is that you happen to need it to do. So what do we need in order to be able to get there? And some of the key technical challenges, kind of continuation of this theme that I'm trying to, we got to find some way to get cost out of the power electronics. Got to find some way to increase the power density to get it to the point where we can shrink it down in small enough size. Higher temperature is really very important. We'd really like to get to the point where at least being able to operate in a 200°C ambient, which is kind of what machines can do, to get it to the point where at least it's on par with that. We're not there yet, and that's the problem. We're probably a good 50°C off from that, and that makes a big difference. Vibration tolerant power electronics, to be able to get it to the point where it's not sensitive to being shaken around by the machine or anything that the machine is mounted in. And finally, the issue of reliability. All of these are critical and fundamental obstacles that we have to overcome if we expect to be able to realize the kind of vision that I just described. And what I'd like to do is to discuss just some of the things that are going on that I believe are setting the stage for being able to accomplish that. In order to do that, I'm finally going to get around now to come and squarely address the issue of the technology that we live with today, which is dominated almost entirely by silicon. If this is on a engineers love plots. In this case, we've got frequency and power. And it turns out that there's kind of an inverse relationship, that if the bigger power that you go, generally the lower frequency as far as the switching frequency that you need. And if you line it all up in terms of all the devices we have, you find that on this kind of log-log scale that there's kind of a, they kind of form a front here. Is that just by chance? It's not. It actually is traceable back to the basic characteristics of silicon. It really kind of places a cap, if you will, on what you can expect to accomplish in terms of this trade-off. So what's new, I already kind of gave it away, is that today we are just seeing, as we speak, within the last few years, the increasing maturation of these new alternative types of semiconductors based on silicon carbide, gallium nitride are the two prime ones that are out there. By the way, is not a new idea that somebody just thought of yesterday. It's really taken a long time for the technology to mature to the point that we can now actually capture it and use it in commercial devices. But what it does is it allows us to push out this envelope, which means that, depending on what you want to do with it, it means that you can either operate smaller powers at higher frequencies or operate higher powers and be able to do that at reasonable frequencies. So there's different ways that you can take advantage of this expansion, but it's all good news to the extent that we can actually achieve it. Good news in terms of our objectives of trying to particularly increase the power density. In fact, that's what I'd like to talk about. And why does that make a difference? Bottom line is that if we can switch faster, in general, and this is pretty generally the case, it means that we can get by with smaller passive components. What do I mean by passive components? I think you know. Talking about the capacitors, inductors, and any kind of power electronic circuits always has those. Higher in frequency can go, if you double the frequency, more or less, there's an inverse relationship. So double the frequency and you can reduce the size of those passive components, which are often some of the biggest components in the whole converter, to reduce those dramatically. So increasing the frequency at which we can switch is generally a good idea if we can do it. But guess what? There are always trade-offs. The other thing that we can do that often doesn't get as much attention is that wide bandgap devices have wide bandgaps. And what that means is it makes them very eligible for higher temperature operation. There's already been cases where silicon carbide devices have been shown to be able to demonstrate their semiconductor action at temperatures as high as 600°C, way beyond what we were talking about. So what's holding us up? The problem is that if you have the chip, there's still everything else that has to go with it. And the folks of you who are associated with poets, I see a couple of you out here, know what I'm talking about. It's everything else. It's all the interconnection, the so-called quote-unquote packaging. Packaging is a name that just sounds like what we're talking about, putting in a box or something. Actually, it's a very exquisite technology that has to go on to take that chip and to mount it in a structure and make the connections to it in such a way that we can actually use the device in the real world. And it's that packaging that often is really the limiting factors in terms of temperature, vibration environments in which we can survive. And today we just don't have the packaging, at least at a price that we can afford, to be able to accomplish this. And that really is one of the big challenges. But it's waiting for us. The basic power semiconductors say, yes, I can do this, if only we can figure out the packaging in order to be able to achieve that. And what's the bottom line? It means that we can take something this big, and if it's the same amount of heat, generate it in this, at a higher temperature in this much space, or it's a possibility of being able to operate equipment in higher temperature environments. Either way, it's a big advantage for us. So this issue is not only for motor drives. I'm a big believer that this is an area that doesn't get sufficient attention, because whether you're talking about motor drives or whether you're talking about lighting, again, LEDs generate heat. We kind of put them into tight sockets. Those have to survive in high elevated temperatures. Solar PV is another example of, again, it's the photovoltaic array that gets the attention, but behind that is power electronics, which has to sit out in the Mojave Desert or whatnot and be able to operate. And particularly if you're talking about this so-called micro inverter configuration, where each one of these arrays has its own inverter, you really would like that to be able to sit out and bake in the Arizona sun or sit in the cold of winter and be able to keep smiling and keep operating for 20 or more years without failures. So the opportunities for wide bandgap is leaving the door open, available for us if we want to really pursue it and tackle it. What I'd like to talk about is an approach that we have been pursuing as far as looking ahead for motor drives. It's a concept that we called integrated modular motor drives. Why do I add the modular in there? Well, basically the idea is that if we have a machine, we split it into segments, like taking a pie and dividing it into slices. Each one is made up of a steel pole with a winding around it. It has its own power electronics associated with it that switches and delivers power, alternately delivers and removes it from the device. And we have, in this concept, each one has its own controller. That together, if you put those together, you have essentially one building block. So the idea is you can get the picture that in this case, if I take 8 of those, build them into an annulus, there I have not only the machine, but I have the power electronics as well. The idea is to be able to do this in the name of being able to ultimately be able to take advantage of the modularity for a combination of reasons, whether it be for fault tolerance or whether it be, we believe in the long run, by modularizing it, that this opens the door for improved manufacturability and longer cost, lower cost. I mean, right now, the cost of the power electronics has been coming down pretty dramatically, and I'm convinced that it's going to continue to do that as the volumes go up and up. Conversely, the cost of copper and commodities, if anything, has been going up. And so the opportunity to build this kind of system, even though if you look at it, there's more power electronics, I believe in the long run is going to turn out to be the better solution. We've gone through actually 3 generations. I'm not going to bore you by showing all 3. This is the second of those 3 and really demonstrates the concept. Guess what? This is a 6-phase machine. You can see 6 of these segments. This is using conventional technology, so each one of these is not that compact, but each one has a separate phase leg based on Igbts. Each one has its own controller. The idea being that if a controller goes out in one of those, that the whole drive doesn't have to shut down. That in fact, just that one slice can take itself out of action, and the other 5 phases can continue operating. In fact, they can actually kind of close ranks, if you will. So unlike internal combustion engine, if you dropped out one cylinder, and that does happen every once in a while if something goes wrong, you expect kind of a rough ride because you're losing that torque during that interval. In this case, by adjusting the gating, we can actually smooth out that torque again and do it electronically rather than trying to do it by adjusting valve striking in a conventional vehicle. Here's what the thing actually looks like. But still, this is clearly a laboratory demonstrator and not something that's ready for prime time. But then along came, in the sequence, the increasing maturity of these devices. And it's getting to the point these days that they're available all the way down to really very low voltages and power levels, all the way up, believe it or not, to devices that can handle 10 kilovolts, which is very high for silicon. So you can get silicon devices that can handle 4,000, but here we're talking about devices that can handle over more than twice that voltage. Again, that wide bandgap is really the key to achieving that. But the point is that these devices are now becoming practical for us to actually put them to work in applications such as this motor drive. And it's made a big difference in terms of the third generation of what we did in terms of being able to demonstrate just how much and how far we could go by adopting, in this case, gallium nitride devices, raising the frequency, and using the power of the new technology in order to shrink its size. And this is what you get. This is still using kind of conventional technology in terms of power converter configurations, but you can see that just how far we've come. I mean, this is truly starting to get to look like a case where we've got the machine, and yes, the power electronics is here. We kind of taken off the hood so that you can see it. I mean, frankly, as I say, if we cover it up, you say, well, that's just a motor. But the point is, this is a demonstration of what you can do. In this case, the thickness of the power electronics is about 1.3 centimeters. I want to give credit where it's due. This was actually work done by my colleague, Professor Ye-Hui Han, and one of his graduate students. And I really respect the job that they did in demonstrating. This is a couple years ago in terms of what was available when GaN devices were much more limited than what they are today. The point is that, that it's tempting, as it always is, when a new device comes along and you've got your power converter, say, well, we know what to do. We'll just take out the devices that are in it and drop the new ones in. What could be simpler than that? What more obvious to do? The problem is that that's not always the right answer. And in this case, if you do that, and you can do that, as I showed, there's cases, there's some issues that you buy. One is the fact that these devices switch so fast that even a short cable about this long looks like a transmission line, which means that you can have to talk about reflections, and you can actually get voltage overshoots that can be double or even 3 times what the voltage is at the inverter end. By the time you get down to the machine, it actually can be 3 times as high, which isn't good for the machine or its insulation. And that's something that comes about because of the fact that these devices are just so good, can switch so quickly that they actually generate this problem. There's issues having to do with fault vulnerability. This is actually, in fairness, isn't a new problem, but it turns out, particularly with permanent magnet synchronous machines, this kind of inverter turns out to be a really bad match because of the fact that it creates some significant vulnerabilities that I'll say more about a little bit later if you're unlucky enough to, say, have one of those switches fail. So it does nothing about that. And EMI, again, it's really kind of a disaster story because it's fast switching. For any of you who've dealt with this issue, you know that there's a very tight correlation between how fast you're switching and the EMI that you're going to generate. And that electromagnetic interference is really critical in terms of being able to use these devices in the real world. So it's not something you can just brush under the rug. And again, be careful what you wish for. If you take your first power electronics class, you say the perfect switch, ideal switch can switch in 0 time. Be careful what you wish for, because if that's the case, you're putting yourself in a place for incredible amount of EMI that becomes very difficult to deal with. And that's what you learn, maybe not in the very first class of power electronics, but as you go along, you find that there are these very real-world issues associated with this. And wide bandgap, if you're not careful, just aggravates that in a very significant way. So what do we do about that? In order to set the stage for this, and I've already given away where I'm going with this, I'm going to, again, kind of go into a 101 stage here and remind or introduce you to the concept that basically the world right now is dominated by what's referred to as voltage source inverters. That is, we have a voltage source, stiff voltage source here. We're converting it into 3-phase voltage that we deliver to the machine. Now there is this kind of dual world in which there is such a thing as what's referred to as a current source inverter, where the idea is that rather than having a voltage source, we have a source that behaves like a current source. In fact, this inductor that you see here, well, there is the points out the duality. In the case of the voltage source inverter, it's the capacitor that helps to stiffen up that bus. As electrical engineers, I hope that sounds pretty familiar. In the case of the, I guess I went too fast, the inductor, that's what gives the current source inverter its current source characteristics. So there are some fundamental differences. The other thing that you might notice is that if you look really close, you'll find that in this case, each of these switches has a diode reverse across it. And you say, well, okay, does that make a difference? In the case of the current source inverter, they're gone. They're not there. So hold on to that thought. That's going to turn out to be a significant issue. That being said, on this case, because of the fact that we have an inductance here and the machine is inductive, it turns out that we need to have at least some capacitance in the case of this 3-phase capacitive filter connected to the output. So what I've done is I've introduced you to the major differences between these classes. And the case that I'd like to make is that because of the characteristics of these new wide bandgap devices that are showing up, is that it turns out that there's arguments to be made for their very attractive suitability for use in current source inverters rather than in voltage source. So in order to introduce that, again, I'll say a little bit in background. There are some benefits of age. And one thing that I'd like to introduce you, and again, bear with me as I go back in time. When I first came of age back in the 1970s, actually the world was dominated by these thyristors. You can only turn them on, you have to wait for the circuit to turn them off. But it turns out that one of the features is that they can tolerate being able to block voltage in both polarities. It's not hard to do that with thyristors. And as a result, it turns out that they're very well suited for current source inverters. So these are a couple schemes of major classes of converters that I grew up with. They're both current source inverters. They really dominated the landscape when it came to adjustable speed drives well into the 1970s. But then what happened? A new kid came on the block. It was still silicon, but so-called MOS-gated devices, the devices we take for granted today. Igbts, power MOSFETs came on the scene, and they were not entirely mature. They took time, but the bottom line is that these devices, their characteristics were quite different. In this case, like it or not, in the case of MOSFETs, the way they were built, they could conduct current in both directions. In one case it was controlled, the other case it was a diode. In other words, there's a built-in diode inside these devices, and frankly, they really could not be easily built to be able to withstand reverse voltage. So this is kind of a dual kind of device that has bidirectional current, but only standing off voltage in one direction. So you can say, well, this sounds pretty academic. Does that really mean anything? Well, it does, because it turns out that the characteristics of these new, at that time, new devices are very well suited for voltage source inverters, but not for current source inverters. And that sets the stage for what was actually a pretty battle royale in the technology world between these two technologies, the incumbent and the new kid on the block. Well, the new devices, because we could turn them on and turn them off at will, we could do it much faster than devices, in the end, this is what won. And so kind of like the dinosaurs, not because of an asteroid, but for different reasons, the current source inverters kind of faded in the background. They never disappeared entirely, but they're back in the background. You might say, well, isn't it, and basically you're talking about the difference between devices that can switch rather slowly and have a pretty large inductor, instead replacing it with these devices that can switch at a much higher frequencies and turn them on and off at will. So it was really, ultimately, it was no contest once these devices gradually matured. You could take those devices, you say, there must be some way we can take these devices. Isn't there some way we can make them work in a current source inverter? Yeah, it's kind of a kludge though. You can actually build in each one of these switches, build in a diode, and that gives them the ability to block reverse voltage. But that's not very pretty or attractive. I mean, you've got another voltage drop, makes it less efficient. So basically the bottom line is that even though you could do it, using these devices, nobody in practical terms really was very excited about doing. So this technology kind of faded away into the landscape, and only a few people really pursued it and did some very good work, by the way, but nevertheless a very, very niche kind of technology. So what's new? Why are we having this conversation? Well, as I say, I'm making the case that because of some of the new characteristics that are becoming available, because of the wide bandgap devices, I'm making the case that current source inverters give us the opportunity to tackle some of the issues and make some significant improvements that the voltage source inverter cannot do by itself, both in the areas, and I'll touch on almost all of these. EMI, I already talked about, mass, having to do with power density, high temperature operation, PM machine fault response, and efficiency. All of those are issues that you can conceive of, and some of these are yet to be fully proven in a way that has captured everybody's imagination. But I'm here to plant the seed that there's certainly something here to take very seriously. So why is it that these wide bandgap, I'm claiming it. If you look at a cross-section of a GaN, a so-called HEMT device, high electron mobility transistor, basically what you find is built as a so-called lateral device, and essentially by having the two major terminals, source and drain, and the gate, we can cause this layer to become conductive and have a low a very low resistance channel between the drain and the source if we apply a gate signal. And when we remove it, it goes back to a blocking stage. Something you notice, though, is that in this case, this device is largely symmetrical as far as the channel. And it turns out that it's as happy to conduct current in one direction or the other. It has no trouble being able to have control of the current in both polarities. Also, because of the way it's built, there is no native or innate body diode that's built into this device. So a couple of the issues that kind of separate out the Igbts, this device is a candidate for being able to avoid that, making it an appealing potential candidate for the kinds of applications that we're talking about here with reverse blocking. But we do need that reverse blocking capability. One of the ways you can get that is either discretely or monolithically, and that's the important point here. Here's the equivalent circuit. The equivalent circuit is two choices. One is you can take two of these, two discrete devices, if you're going to do it that way, and connect them in anti-series. That is, turn one of them around, connect them, in this case, by the source. The nice thing about that is you only need one gate drive, and you can, and you have a device that actually has the capabilities, can block reverse voltage, as well as being able to control the current in the other direction. You can actually switch it around, so have these two devices and connect them up at their drain, so-called common drain configuration, and both of these are candidates. There's been work, some really clever work in terms of how we can take discrete devices and package them in very compact ways so that we have the least possible penalty from having those two devices rather than one. Obviously, what's even more appealing and what really we need is the availability of monolithic devices that can accomplish that. And these are in the process of working their way through out of the laboratories as we speak. In fact, I use Panasonic because they're probably the most advanced. They actually have announced and have demonstrated some experimental results using devices, monolithic devices that have these characteristics that are rated at 1200 volts and 100 amps, which is not shabby for this kind of technology. So the technology is still, and there's several other device manufacturers that in their back rooms and their skunk works have projects underway to explore their own versions, maybe not quite like this, identical to it, but configurations that are going. So this is a case that technology is still in the process of evolving, and this is a key piece of the puzzle that takes place. So if you were to do that, you would take, whether these are monolithic or done discretely, you would take 6 of these. In this case, this is shown with the bus split between these two buses. You can see again these filter capacitors. And what we can do is implement it this way and take advantage of the fact that these devices can switch very fast in order to be able to start to unleash some of the real advantages that we have, because both this bus inductor as well as these capacitors are both candidates for having their size shrunk by being able to increase the switching frequency. In fact, now, as you can see, I'm gradually getting deeper into this. For those of you who are really pretty new to this area, please bear with me. This starts to get into a little bit of an area that for those of you who are specialists can perhaps relate to a little bit better, but I'll try to at least get the concept across as best I can for all of it. This is showing at the output terminals of the inverter what the voltage and current waveforms look like for these two types of converters. Voltage source inverter in the left column, current source inverter in the right column. Upper row are the voltage waveforms. Lower row are the current waveforms. You see that as far as the currents that come out of the inverter and delivered to the machine, they're actually quite high quality in both cases. Now, some of you may chuckle that are working in this field to see numbers like 200 kilohertz. For those of you new to the area, typically the switching frequencies with Igbts are more in the range of 20 kilohertz, something that's above the audio range, but more in the range of 20 kilohertz. 200 kilohertz is just pretty much so out of the question using silicon devices. But with today's GaN, gallium nitride, and silicon carbide, at least for a drive of the size like 3 kilowatts, we can seriously talk about being able to switch 10 times that speed. So if you do the math, that suggests that we can get some really significant reduction in those passive components. And that's exactly what's happening. So there's not much difference here. You can say, well, okay, where's the advantage? Well, the advantage comes when we start looking at the voltage waveform. At the output of output of an inverter, it's switching between those two buses. So if your input is 600 volts, every time that device switches, and it's doing it 200,000 times per second, it's switching between those two levels. These edges, again, getting back to what I said, are just prime candidates for creating these overvoltage issues and the EMI. So what's different? When you look at the current source inverter, what is this? Still looks like a sinusoid. How does that happen? Well, it happens because of those capacitors. We need them, they've got to be there, but they're doing something for us. It means that the output of this no longer is this big chopped up waveform that gives us so much grief, but instead is exactly the kind of waveform that we'd like to be able to deliver. And it comes naturally with the current source inverter. Now, some of you may say, but wait a minute, you know, if we got that filter, I can add a filter at the output of the voltage source inverter as well, and you can. The problem is, if you're going to do that with a voltage source inverter, each one of them has to be an LC that you have to add into it. You can't get by with just a C because you've got a C at the front end, so you need to have an LC. So it's not as easy to be able to achieve that, or at least you have to pay a price in terms of mass, cost, and volume in order to achieve that. So this is what happens ideally, actually. It actually gets worse than this. Because of this switching, what I'd like to show is, in fact, in the real world, everything has capacitance, everything has an inductance. And the higher frequency you go, the more all of those parasitics really become out of the woodwork and really bite you in the behind in a bad way. Some of you know that only too well if you're dealing with these kinds of devices. So when you include these in even a simulation, what you see, and this is just pointing out the presence of some of these parasitic components that I say are everywhere. Between the leads, there's parasitic inductances as well as capacitances to ground from within the machine as well as from the leads. When you include those in, what you find is that, and this is, in this case, we're demonstrating the impact of these parasitic capacitance, we find that something has changed here. Now, in particular, if we look at, if you look at these current waveforms here, we find that now the current that's being delivered by the voltage source inverter all of a sudden now has all this fuzz on top of it. All of these are current spikes. We have to charge up those parasitic capacitance and discharge them with each switching event. And that can be an incredible source of EMI as well as an additional source of losses. In the case of the current source inverter, because we're exciting it still, despite the presence of those parasitics, given the fact that the output of the inverter is a sine wave, there really is very little impact of that switching in anything like this way. So again, we're starting to see the power of the current source inverter in order to inherently provide some advantages when it comes to the EMI and the potential problems of voltage overshoot. Here's a more explicit look at the EMI, and again, start to get a little more specialized. This is over the frequency range at which their specifications exist today for EMI, from the range from 150 kilohertz up to 30 megahertz. And this is given in terms of common, we're looking at common mode EMI, again, specialized, but a particular form that is particularly nasty in many types of devices. And what you can see is here's the baseline. This aqua one here is for a voltage source inverter operating at 10 kilohertz without a filter. And so that gives us a floor. It turns out that when we switch at high frequencies, it's true that frankly, regardless of whether it's CSI or a voltage source inverter, there's going to be an elevation. That's hard to avoid. On the other hand, what you can see is that, again, because of the combination of the DC link inductor and those filter capacitors, we see a roll-off that is significantly dramatic, more dramatic in the case of the current source inverter compared to the voltage source inverter without a filter. And again, I'll freely admit that if you add a filter to the voltage source inverter, you can drive that one down, but it's at the price, literally, and in several different directions, impact of adding that filter. In fact, if you do the mass roll-up, what you find is that regardless of whether it's a voltage source inverter or current source inverter, if you can switch them at 200 kilohertz, you can achieve some pretty impressive reductions in terms of the mass. This is a roll-up that we did, and it basically says if you start off with our baseline, today's technology, silicon devices, voltage source inverter, 10 kilohertz, what you find is, in this case, something like 1.5 kilograms. And this is for a 3 kilowatt application. If we apply the technology, and here again are the three choices. If we talk about a voltage source inverter without a filter, or a current source inverter doesn't need a filter or anything beyond, we find that actually they're a pretty comparable. Current source inverter we see as a bit of an advantage, but frankly, if we could stop right here, you'd say, well, there's not necessarily that big of a difference. But the point is, you can't stop here. In the case of the voltage source inverter, you really are pretty well forced in practical applications to add that filter, and that, again, adds mass, and as you can see, puts it at a disadvantage compared to, again, better off than where you started with, but not as good as what you can get with a basic current source inverter. So again, puts and takes that have to be borne out. Current source inverter, though, gives you a pretty good package of these advantages that are very important for us to be able to achieve the objectives. And again, this filter is a particularly nasty thing that, again, anybody working in this area knows that often the EMI filters can be the biggest component of all in the converters that we build. So when we look at high temperature, you might say, well, is there any difference here? And the answer is that there is. Capacitors tend to be often the limiting factor. And even if we use a more advanced, say, okay, we don't want to use electrolytics, so we'll go with film capacitors. That's kind of the state of the art that's widely used in many converters today. Those devices still have limits of about, even if you buy a relatively high temperature of 180 degrees C, and you're paying a premium even to get up that high. So that's not as far as where we want to go. What if we get rid of that capacitor and instead replace it with this inductor? It's not hard to build an inductor. Inductor really has the same technology as the machine, so we can build those to get up to over 200 degrees C. But then you can say, wait a minute, you've got capacitors there, so aren't you subject to the same thing? Bottom line is, if we're operating these at the frequency we're talking about, these can be ceramic capacitors. So you don't need much capacitance, and ceramic capacitors have the desirable capability that they are available, again, at temperatures that are in this range that we want to get to. So again, if we're dealing with the high temperature, the bottom line is we can't only focus on the device. We really should look at the converter topology and say, let's pick a converter topology that is better suited to high temperature operation. And my claim is that the current source inverter has the advantage in that category. So this gives you an idea of kind of the kind of vision that we have underway. And we're in the midst of a contract right now with ARPA-E in order to pursue concept. And this is just a cartoon, obviously, but it gives you an idea of what we're trying to get to. And as you can see here, this is just a suggestion that we could use a toroidal inductor mounted circumferentially around the concentrically around the shaft. But you don't see any big inductors. You don't see much of anything. The inductor is the biggest component that we have to wrestle with. But again, we can take advantage of the fact that if we're switching at 200 kilohertz, we can shrink that down to a fraction of what it otherwise would be if we were using conventional technology. So what about this fault mode response? I alluded to this, but I do, before I'm done, want to say a little bit more about this, and I'll try to wrap this up pretty quickly here. It turns out that there are a major difference, and again, the bad actors, it turns out, are these diodes in the voltage source inverter. In the case of the current source inverter, there's an inductor, but no diodes, and that turns out to make a big difference. If we short the terminal or have one switch fail in an inverter of a voltage source inverter, we're subject to currents that can be 3 times higher than rated current or more. It's a very serious conditions, and those don't go away as long as the rotor is spinning because of the back EMF of the machine. On the other hand, in terms of the current source inverter, provided that we recognize that failure has occurred, we can open up remove the gating from all the remaining switches and essentially extinguish the fault, nip it right into the bud. This is actually experimental results that we have that demonstrated our ability to be able to tolerate what would otherwise be a very dangerous fault for a voltage source inverter and turn it into something that is much more benign in the case of the current source inverters. So I'm a big believer in the fundamental advantages that current source inverters have for this kind of application when it comes to fault tolerance and ability to withstand partial failures. Now, I could spend some time here. I'm not going to have time. And this is always dangerous territory, by the way, to try to make comparisons between different technologies. Again, this is the baseline voltage source inverter using today's technology. This is the voltage source inverter, 200 kilohertz with a filter. So this says, let's get ourselves on the same playing field in terms of the EMI envelope with the current source inverter, switching at the same frequency. And you can see that actually in terms of EMI and efficiency, there's significant advantages that you can get to by going to wide bandgap with either of these two. The problem is that because of the limitations I described in terms of the mass and the high temperature operation, the voltage source inverter is at a disadvantage compared to the current source inverter. And particularly in terms of the permanent fault response or the permanent magnet machine. Voltage source inverters are just really tough to deal with. And current source inverters in comparison give us the tools of being able to escape that box. The one areas where right now the jury's still out is how long is it going to take to get to these monolithic switches. If we can get to the point where we have monolithic switches, we believe that we can turn most of these boxes here into green. But it's always trade-offs. I'm the first to admit that. But there's at least, I believe, and we're demonstrating it, real promise that comes along with pursuing the vision that's based on this current source inverter. So finally, future directions. The issues of advanced power semiconductor packaging, high temperature components, advanced thermal management, all of those need to get done. Advanced power converter integration technology based on more advanced concepts of integration that take advantage of the third dimension. Higher levels of of converter integration, how we can compact this even further. Improve modularity to simplify manufacturing. These are all concepts that can take advantages of, and the point that I wanted to make here is that if you really think about these, all of these really depend on a new breed of truly a multi-physics, multidisciplinary kind of approach that's needed in order to accomplish this. And that's really one of the challenges for us as instructor. It's one of the challenges for those of you as students to step up to these challenges, to be able to address these sorts of things. Bottom line is, in the end, there always are competing demands. Efficiency, thermal management, cost, power density, reliability. Things that you do to solve one by using devices that can stand higher temperatures, that can be a negative impact on cost, and so on. So certainly we have our work cut out for us if we're not able to settle for just one of these, that we need to achieve all of these simultaneously. And that's our challenge. That's what we're paid to do in order to, over the course of our careers, find ways to tackle those. And this is what the future holds for any of you who are set to tackle it in this area. There's new technologies, no doubt, such as additive manufacturing, that already are being explored, but are nowhere near their full potential in terms of exploring what they could mean for advanced packaging. And it's this synthesis of new technologies coming from materials, coming from manufacturing, coming from every possible direction that's going to ultimately make the difference. So finally, conclusions. I don't think you'll be surprised based on what I said. Integrated motor drives, one of the most promising paths to achieve the full potential of adjustable speed drives. Already significant progress has been made, but we're on the cusp, I believe, of making some significant additional advance. Certainly these wide bandgap devices are truly a very major development, and that I've only seen a couple times in my career. Wide bandgap power semiconductors, they really are a game changer, and they play an important role. And I believe, particularly combined with a current source inverter, it's not this alone, it's the combination of the two that makes that vision appealing. But the complete fulfillment of this is really going to come down, as I suggested, to addressing very difficult multidisciplinary challenges. So two things to take away from it. Integrated motor drives, I believe, have a bright future. And the second is, you heard it here first, current source inverters will rise again. So we'll see if I live long enough to see that, but you heard it here first. So thank you very much for your attention. I had to have Bucky at least here once, and at least carrying a lightning bolt here. So thank you very much for coming today.
Thank you so much, Professor Jahns, for that wonderful presentation. So do we have any questions?
Thank you for a wonderful presentation. I do have a quick question. As you seek further integration, can you speak to challenges with electromagnetic susceptibility coming from the electric machine, coupling into the power electronic gate drive circuits that you have so closely coupled?
Yes, there's a whole variety of issues. I mean, EMI is an equal opportunity. I mean, you're concerned about how much is emitted, but you're also concerned about what happens on the incoming side in terms of what the impact is there. And again, I think looking out to the longer term, there are really some exciting things that are happening. In fact, I have to give credit for Panasonic. If you go back and look at some of the same papers that discuss what they did with the drive using their new monolithic devices in the converter they put together, the same one describes, for instance, using an optical gate drive, not only for passing the signaling, providing the galvanic isolation, but actually for providing the power as well. And so it's just an idea. I mean, that's kind of a technology tour de force, not ready for prime time in terms of in the field, but it's just an indication of the fact that on the horizon there are technologies out there that are very EMI tolerant in order to be able to deal with these. And that's what we're going to have to do. Again, we're going to have to use all the tools in our book to combine advances in optoelectronics and optical world with what's going on in our world and what's going on in some of the other areas I described in order to be able to tackle these. So there's no one answer for that. It's going to have to come from materials that are better at providing shielding. That's going to be important for radiated, and it's going to come from a variety of clever circuit techniques and uses of alternate technologies that I think are going to be the breakthroughs that we're going to need. But yeah, that's not going to go away. EMI is something that is doesn't, frankly, in many cases, doesn't get the attention it deserves. And I think for those of us who are working in this field, there's going to be no choice but to pay more attention to it because it's going to dog us in ways that it never has up until now, because we've only had 20 kilohertz. But if we're talking about the kind of frequencies we are now, as I say, issues that were only a problem if you had cables about the width of this room are now becoming problems with cables that, guess what, about 1/10 of the length that they were before. And so it really is bringing down these issues to, so with opportunities, go challenges. That's the way that it always has been. It's certainly the way that it is in this case as well. So thanks for the question.
Any other question?
Are there any reliability advantages to using a current source converter as opposed to a voltage source converter?
I believe that there are some, indirectly in the sense that that's going to be time that we're going to is going to be required in order to be able to work that out. There are, issues, failure mechanisms that go along with the switches, and frankly, wide bandgap devices are so new that frankly, it's a little bit hard to say for sure whether the devices themselves, wide bandgap, are going to end up being better than the silicon devices that they're replacing, particularly given the fact that a lot of work has gone into silicon. It's the incumbent mature technology, and it's always tough to knock an incumbent technology off when you're kind of the new kid on the block. That's going to be one of the challenges. But I think the other part is to look at the issues associated with the passives, because temperature has a lot to do with reliability. And so if we have devices that are inherently more tolerant of higher temperatures, Arrhenius says that we're going to have that on our side. That is, that we're going to be able to operate at a higher temperature with these devices at temperatures that would pose problems for the bigger problems for the capacitors and some of the other components. So I think that is the best one I can articulate right now. But the other advantage I'll just say is that inductor, there's good things and bad things about having it there. But one good thing is that if some bad thing happens, one thing as elementary electrical engineers, you know that V equals L didt. So if you have a fixed voltage and any inductance, it means it's going to limit the rate at which the current can increase. And that buys you time. It buys you time to respond to it with a protection circuit in order to be able to shut things down or protect it in a way. So that, combined with the issues I described as some of the fault tolerance, it's a complicated story, but I do believe when you put it all together, it does add up to some net potential advantages. I don't want to overplay that because the proof has got to be in the pudding, but at least there's some promising factors there that I believe that fall into the column of the CSI compared to the voltage source inverter. But the VSI is the incumbent technology, and there's no getting around the fact that it has a big head start in that. And so the new kid on the block, it's our challenge to demonstrate that we can not only match that, but exceed it, and time will tell if that's the case.
Any other question? Perfect. Let's give a big round of applause for Professor
Thanks for
Jahns.
coming.
Thank you so much for coming here.